All right. Um, my name is James Gann. Today, I'm presenting my project, Cheeks, the AI companion. So today on my agenda, I'll be going over what is my project, the project timeline, the block diagram, how does he move, how does he see, how does he think, and then I'm going to be going over my PCB versions and updates, final pictures and demonstration, and then any questions at the end. So what does Cheeks do? Cheeks is an AI companion that will respond to any question you have using its AI API Qwen 2.5. You start by putting your hand right above his head. He'll jump up and down twice, signaling he's ready to go. After that, you ask your question. He thinks for a little bit and then answers to the best of his hamster abilities. So this is my project timeline. Anything in the blue has to do with kind of the PCB and circuit boarding. So that was testing and then ordering the final board and kind of assembling. Anything in the pink is the housing, and the red is kind of putting everything together, final things, and then the yellow was my presentation. So the first kind of progress one, and then the final one, which is right now. The green was the user manual. So this is the block diagram. He plugs right into the wall using a DC power supply and powers the Raspberry Pi. From the Raspberry Pi, everything is centrally connected to that. So it has the motor controller, which controls his movement, so up and down, and also the analog to digital converter, which is used for the motion sensor. That's kind of like how he knows your hand is right above his head. And then the microphone and the speaker, which is the input and output sources, is connected via USB. So how does Cheeks move? Cheeks moves using the L298N motor driver. You put it right in the middle between your GPIO and motor driver, and it kind of gives it a little help. So you connect the GPIO pin to one of the inputs of the motor driver there, and you use that to tell the motor when to go instead of trying to power it with the 3.3 volts that the GPIO, which is the general purpose input and output, sends out. Motors need a little bit more voltage than that, so you give it a base voltage for it to work off of. How does Cheeks see? So the sensor circuit is using a photodiode and a photosensor. The photodiode sends out an infrared light, and the photosensor then picks it up. So it's kind of like a TV remote in your TV. Depending on how much light the photosensor receives, it reads out a certain voltage. So then from there, the analog to digital converter, the ADC, takes the voltage reading anywhere from 0 to 3.3 volts and converts it to a number anywhere between 0 and 1023. With that number, you can then use it as a value in your code to kind of use it as like a threshold. So it's like if it's over 800, then do something. If it's under 700, you could do something else. How does Cheeks think? So Cheeks records your voice using the Whisper AI and turns it into text. The words then get sent to Qwen 2.5, which is the AI inside of Cheeks. Qwen uses 500 million parameters. Just to kind of put ChatGPT uses 52.5 trillion parameters. So compared to ChatGPT, he's not the brightest. Piper, which is the text-to-speech program, reads the response from Qwen and Cheeks, and Cheeks talks back to you. So my PCB versions and updates. Starting with the V1, it was unnecessarily big. Had some extra components that I wasn't really sure if I needed or not, and some incorrect footprints. V2, I fixed everything. footprint wise and made it smaller. I used this one for testing, and the way it worked was a daughter board, so I kind of had it just bridged over with some wires to the Raspberry Pi. Then for my final design, I made it a Pi hat, so you just kind of squish it onto the GPIO pins that way, and it works by giving power to the 5-volt pin through the barrel jack there, powers it on. So here's some final pictures. The first one is kind of a close-up of his face. In his right eye, you can see the kind of the emitter and the receiver. And then on the right side, sorry, you see kind of the Raspberry Pi, the PCB, and a cooling fan with the motor driver too. That's kind of all that's inside. So let me turn it on. It does take a second to kind of boot up. Give it a couple more seconds. All right, so I'll try holding my hand and then speak into the microphone here. Oh, not ready yet. How's your day today? So he's going to think for a little bit.
Thank you. Enjoy your day.
So obviously it's not the smartest, but it does use AI to work. So you can ask it any question. Let me turn it off there. Any questions from the crowd? All right. Thank you, guys.
The microphone right here. You want it very close to the Yep. And just right on the wall.
Hello, my name is Kyle St. Pierre, and today I will be presenting my project that I've been working on all semester, the laser tripwire alarm. Project overview. So, my project was a laser-based intrusion detection system. It detects the beam when it is interrupted using a phototransistor to sense the laser, a microcontroller to read that signal, and a 555 timer to produce an alarm. It has a keypad for disarming, and on a reach, it will produce an alarm. The whole system runs off a rechargeable battery pack as well. Moving on to my timeline, this shows the progression of the project. I first started with choosing a project, researching what I could do. A laser tripwire was one of the first things I found. After that, I looked at components. I did a basic design on some paper, some circuit schematics. Then I prototyped my board and made a PCB. After making my first PCB, I got some feedback. And the main change between my first PCB and my final PCB was adding in a common ground. The common ground helped to allow both the phototransistor, which has a setup in a voltage divider with a 4.7 k ohm resistor, and my 555 timer circuit to communicate properly. After that, I made my user manual and made my final presentation, which I am giving right now. So the most important part of my project is this phototransistor. It is a light-activated transistor that takes in photons to generate a base current. Like I said earlier, it uses a 4.7 k ohm pull-up resistor to pull the voltage up to 3.3 volts. And with the laser on, it gives 3.09 volts. And blocked, it gives 0.33 volts. Now with this, I get a clear digital signal of a high and a low. Moving on, I'll talk a little bit about sensor performance. So when I originally designed this, I designed it for a phototransistor. The phototransistor takes in light and its resistance changes. The problem with this, which made me switch to the photo transistor, is it had a large variation in the voltage it was producing. And this was due to the ambient light. So if you can see on this table, when the room lights were on, it produced 2.9 volts and 1.07 volts when the laser was present. These were pretty good readings that I could use to have a good digital signal, but however, when the room lights were off, it produced 3.3 volts when the laser was blocked and present. And obviously, you want your alarm system to work when it is light and when it is dark. So that's one of the reasons I changed to the phototransistor. The phototransistor I used was the BPW85. This phototransistor allowed me to get clean digital signals, 0.332 volts when the laser was blocked, and 3.09 volts when the laser was present. Moving on to the second most important part of this project is the software. The software has 3 different states. The disarm state, the arm state, and the alarm state, and it runs off C code in a state machine using these states. So in the disarm state, you have the option to set your pin for your alarm, then you can arm it. Once in the arm state, the microcontroller continuously reads the signal at the PA0 sensor input, and this input then, once it becomes a low, triggers an output at PA8 to trigger the alarm. Now, this software also has code in it for the keypad and OLED display, which allows you to interact with the alarm system. Yeah, moving on to the current status of my project. So my project is fully functional, the sensor detection is working, the keypad control is working, and the alarm is triggering correctly. However, due to the phototransistor being very sensitive, I was not able to make a demo today. I tried for 2.5 hours yesterday trying to get the laser to bounce off a mirror and hit the phototransistor, but I couldn't get it at the right angle. So sadly, I do not have it for you today. If I were to make any improvements on this design, I would definitely add in a enclosure for my battery pack. That is one of the things I didn't get to. And secondly, they make these holders for lasers where you can adjust them up and down, which would have made this process a lot easier in getting the laser to hit the phototransistor perfectly. Any questions? Thank you. Really? I couldn't see it.
What? Yeah. Oh.
Hello, my name is Vance Verossi, and I will be presenting my project, the Volume Forge. Right, so for the agenda today, we have the project description, my Gantt chart. I'll be showing my final schematic and PCB. I will be highlighting two technical details, those being the volume slider software and the touchpad PCB. After that, it will be the project status and time for questions at the end. Right, so project description. The Volume Forge is a desktop audio controller. It's designed to be plug and play, which means you can plug it straight into your computer and it will work immediately. The controls are designed to be simple and fairly intuitive. And the audio controls are supposed to be seamless, so you don't have to fiddle around with anything on your computer to get it to work. Right, so this is my Gantt chart. So it's a timeline of my entire project, which starts with the first circuit board testing and building. And then after that, I was to update my PCB so that it would be ready for a final circuit board. And while that was being printed, I had a website and a user manual project. And then afterwards, I had to build the final board, test the final board, create this presentation, and update my portfolio. Right, so here's my final schematic in PCB. You can see on my schematic where the touchpad and the OLED screen and the buttons hook up to my microcontroller. And you can see on my PCB that I ended up splitting it into 3 boards. I had to do this because the different parts of the board were vertically on different levels. So the buttons stick off the board a bit, but the PCB touchpad part needed to be higher up than the actual main board. So they were split up to make assembling easier and make more sense. All right, so for the first technical detail, I will be covering the volume slider software. I was originally going to use the touchpad as like a grid of buttons. So when you would touch a certain level on the touchpad, it would correspond to a certain volume level. I realized that this wasn't actually as doable as I thought it was because of limitations due to my microcontroller. So I instead opted for a different input, which would be swiping on the touchpad. So when you swipe on the touchpad, it'll change your volume level based on how large of a swipe you did, up or down. And the touchpad itself is a capacitive touchpad. It's on a PCB, which means all the pads themselves are just bits of copper on the PCB design itself. It's a capacitive touch sensor, which means that the copper on the PCB is 1/2 of a capacitor, and your finger is the other half, so it can detect when your finger is touching the touchpad due to the change in capacitance on the PCB. It works as a volume slider, so you swipe and it changes the volume like I already said. Right, so the status of my project, I have the hardware fully operational, software is fully functional, and my housing is complete. And now I will do a little demo. Not sure if it's gonna play the music right away. I guess we can see. So right now my computer is at 0 volume, which is shown by the OLED screen at the top of it. If I swipe up, won't show it on the presentation itself, but I've raised the volume. Now if I press the button, it'll start playing the music. If I press the top button, it'll skip to the next song, and if I press the bottom button, it'll go back to the original song. I can press the middle button to pause it again. All right. Any questions? Thank you.
No, didn't get the audio. Oh, yeah, but okay. I thought it was going to play through the projector output, but I think it has to. Yeah, I think we had to have set it up to go out your HDMI. Yeah. What's that? Yeah, it'll be if you go on the VT lab and go on the line tab. Yes. Oh no, it'll go on the line tab. It'll like any video. Yep. If you go to the line, you can see the line. But it'll stay on the channel. My name is Crystal, and I will be your
Morning. My name is Alex Bishop, and I'll be demoing my and presenting my automated wax grinder, which I like to call the Wax Butler. And this is my sophomore electrical project I've been working on all semester, and it's given me a lot of trouble, but I'm excited to present it for you. So here's my project overview. It is a handheld ski waxing system that's designed to melt the ski wax using the iron, and the mechanical part of it is that it's fed using a motor-driven rotary rasp. The control wax feed, you control it electronically using a potentiometer, and it is designed to apply wax more consistently than hand waxing, reduce the number of manual steps in the waxing process, and it has an overcurrent shutoff function for safety. So the project goal here is here's a picture of it, is to make it faster, more consistent, less labor intensive, as well as easier for beginner users, and it's more repeatable from ski to ski. It is basically it's very linear. That's the main purpose of it. Is it's not like, you know, you take a brick of wax, you put it up to the iron and drip a bunch. You can waste a bunch of wax doing that. This is designed to evenly disperse it over the ski in a linear way. So my first technical detail is my control electronics. It uses an Arduino Nano for system control, a potentiometer for the motor speed adjustment, an IRLZ 34 MOSFET for motor control, a 1N4007 diode for back EMF protection, and a 6-volt power system for motor drive. The overcurrent shutoff system is made possible by the ACS 712 linear Hall effect sensor. So, second technical detail, the wax feed mechanism. This is a very mechanical part of it, and it took me the most time of anything, just because of the housing, had to be able to deal with so much torque from the motor. It is a motor-driven rotary rasp, which is paired to, the whole system is a motor, which is paired to a coupler, which is then paired to a ball bearing and a rotary rasp. And I had to find a way to fit all these perfectly using just PLA off of a 3D printer. Any sort of non-perfect fit will cause the motor to spin on its own, and the wires can get all caught up, and I had to deal with that a lot. So the spring-loaded retention block is just springs which keep the wax from, or keep the wax tight to the rasp itself. This also was difficult to deal with because of the pressure on the rasp can sometimes make the overcurrent shut off too early, but I've found that it's been pretty successful overall. So how the wax butler works, it's a heated wax iron that melts the wax. A rotary rasp grinds and feeds the wax forward. The motor drives the wax feed system, and it's obviously, as I said before, the spring-loaded pressure keeps the wax pressed into the rasp. And potentiometer will control the motor speed, and the nano manages the system control. So here's my timeline. What I did first was finish the first circuit board. This was very easy. The user manual was also very straightforward. The PCB design gave me some trouble just because of how the MOSFET was giving me so much trouble. I had it in backwards because the schematic. I flipped it in the schematic and did not realize it. But for my final, very happy with the final product, and it works just as expected. The website was relatively easy. I want to do a little bit of updating for it, but everything as of now, including the final presentation, is where I wanted it to be from the beginning. So the efficiency discussion, this is a very important part of my slideshow. I wanted to make it faster and more efficient than hand waxing using this system, but at the current prototype scale, it's not more efficient than hand waxing, but the proof of concept is absolutely there, and it can be, with very minor improvements, definitely better than hand waxing. So here's my demo of the overcurrent shutoff. It will run at 600 milliamps and shut off at 800 milliamps. So here I'll be using a spring, and as you can see, it stops pretty quickly as the spring gets stuck in there. It's very, very little delay, and I mean the spring's it's a very movable item. It's meant to flex, so anything much stiffer will shut off almost immediately. Current status: wax feeding is fully functional. The overcurrent shutoff is completely functional. The motor to rasp mechanical system is exactly where I wanted it to be, works perfectly, and overall my project is complete. The housing, I would love to do some updates on, maybe for the senior project. In conclusion, the prototype is not yet faster than hand waxing, but it has absolute potential to be there. It proved that the automatic wax feeding is possible. The mechanical wax application can be integrated with heat. Electrical control improves consistency, and the concept is absolutely where it should be as a working prototype. I did miss a slide. I'm going to go back to the demonstration here. So you can see it's not easy to see because of how little the shavings are, but it does shred pretty quickly. They're just so small that you can barely even see them. So definitely with a different tool, maybe something that shreds instead of like rips at the wax, something like a sideways drill bit or something of that sort could definitely be great. Any questions? Thank you.
Versus laptop. Oh, I have my laptop. You have one? Yeah, you're welcome to use yours if you have it. Okay. Look at it. So, push and hold this button, it helps you move around the screen. You hold it, then just move next to approximately here. If you go ahead and just that mode, not to do all at once. Yep.
Hello everyone, my name is Kate Hingler and today I will be presenting my audio reactive LED project. So why did I choose to do this project? I wanted to make a product that was interactive, that you could give it an input and it gives you a really cool output. And I wanted something can boost the atmosphere. So if you're listening to music, watching TV, if you have friends over and you're listening to music, you have something that's visually appealing and can boost the atmosphere. And I wanted something that would sit nice on my desk, which is you will see in the housing. So it's really simple on how it works. We have a microphone that takes in audio and sends raw digital data via inter-IC sound, which sends the data to a microcontroller, and then it sends a 24-bit GRB data to the LEDs. For the microphone, I'm using a small INMP 441 module. For the microcontroller, I'm using an ESP32 dev board, and then I'm using that complicated LED title. And then here is my timeline. So the black bar is all signifies completion. So the project is basically done. I just need to finalize my website and then finish this presentation. Here is a schematic. It looks a little complicated, but it's not that complicated. On the left, the big square is the ESP32 dev kit. And then we have screw terminals for power in. So it uses a rechargeable battery pack. So you can set it on your desk and you don't have any cables. You don't need to plug it in. And then we have a switch so you can power the device on and off. And then we have the connection in the top right for the LED power or the LED strip. We also have a microphone screw terminal on the bottom. And then we have a level shifter because the data line for the LED needs a 5-volt high, and the ESP32 dev board sends a 3.3 volt signal, so level shifter keeps it steady. We also have some decoupling capacitors, which are lovely. We also have a fuse, so in case you wanted to disconnect the battery pack and connect it to any power source that could potentially fry your circuit, it is protected. Here's my final PCB board. It's relatively small and compact. You can see the terminals on the sides for easy connections. And we have the top layer, which is all of my power lines, and the mesh layer for that is 5 volts, and then we have the bottom layer, which is ground, where all my ground pins are, and then I have traces on both sides. And then here's my housing that I made in SolidWorks. We have the area for the PCB to screw in, the PCB screw standoffs. I also have LED strip slot, so I have my own component that can go in there. We also have 2 ports, micro USB ports, that you can manually connect to the ESP32 board in case you needed to update the software. And we also have the charging hole for the battery pack, so you can recharge the battery. And then we have a microphone slot, and then the battery pack holder. My rechargeable battery pack is the cylinder, so I figured it would just sit in there nicely. And then the lid is relatively easy. You just pop it on and off. and it has the switch slot on it. And then I use WLED software, which is really awesome. It is made by a cool group of people, and it's made specifically for the ESP32 board to talk to the specific LED strips. It's really awesome because it uses Wi-Fi to connect to it, so you could use your phone. You can use an app on your phone if you wanted to, or you can use it on your PC. And it has a lot of presets. So you can make it any color you wanted. You can even ignore the audio reactive part if you wanted. But it does have audio reactive presets as well, which is really cool. And then here are pictures of the final project. Everything is working nicely. The only thing I would change is probably just keep tweaking the housing so it looks better. And then we can do it. Yeah, you can file changes based on whatever audio you put. Yep. Yep, that is going right behind my monitor. That's